Hello guys, I hope you're doing well today. Today we're going to talk about the bimolecular nucleophilic substitution reactions, or in short we call it the SN2 reactions. Bimolecular nucleophilic substitution reaction is a reaction that involves two molecules in the rate determining step. And such type of reactions usually complete in a single step. So that single step is actually the rate determining step, and this rate determining step involves two molecules, and that is the reason why we call it a bimolecular nucleophilic substitution reaction. So this is a general representation of a bimolecular nucleophilic substitution reaction. So we have the substrate here, which of course is an alkyl halide, and we're going to react it with a nucleophile. You can see the negative charge on the nucleophile, and as a result, when these two react, we get a molecule in which this X, or the halogen or the halide, is replaced by the nucleophile. So a halide ion is released as a byproduct. Let's see the general mechanism for this reaction. As we discussed earlier, it's a single step reaction, and so the nucleophile and alkyl halide both will be involved in this single step. So what happens in this reaction is that the nucleophile, which of course is a negatively charged species, or you can say it's an electron rich species, it will attack any electron deficient center present in the alkyl halide molecule. And as you know that there is a difference of electronegativity between the carbon and the halogen, carbon having lower electronegativity, halogen being the higher electronegative atom, and so carbon will be slightly electron deficient because of the electron pull exerted by the more electronegative halogen. And so nucleophile will fancy attacking the carbon atom that is directly attached to the halogen. And as a result, this halogen will leave in the form of a halide ion, taking this bonded pair along with it. But before that, this whole system goes through a transition state. And as you can see here, in the transition state, the bond between the nucleophile and the carbon atom or the alkyl group is in the process of making, while the bond between this R group and the halogen is in the process of breaking. So this nucleophile is trying to get rid of the negative charge, but it has not completely got rid of it, and we show it with a delta negative sign. And this halogen is going to have a negative charge at the end, but it has not completely gained or adopted this negative charge. So again, we show it with a delta negative sign. So this is how the transition state of this reaction looks like. And as soon as this bond formation between the nucleophile and the R group completes, and the bond breaking between the R group and the halogen completes, we get a molecule in which the R is now attached to the nucleophile and a halide ion is released as a result. Let's see how we can find out the rate of reaction. As you saw in the previous slide, that it's a single step process, and this only step is actually the rate determining step of a bimolecular nucleophilic substitution reaction, or the SN2 reaction. And in this one-step reaction, you can see both the nucleophile and the alkyl halides are involved. So the rate of reaction of a bimolecular nucleophilic substitution reaction, or SN2 reaction, will obviously be affected by the concentration of both alkyl halide and the nucleophile. So if we convert this proportionality into an equation, the rate equation becomes rate is equal to K into concentration of alkyl halide into concentration of the nucleophile. This is how you can find the rate of reaction, and this equation clearly shows that the rate is dependent upon both alkyl halide and the nucleophile. Now let's see the energy profile diagram of this bimolecular nucleophilic substitution reaction. We have seen previously that it's a single step reaction. So what happens is that the nucleophile and the alkyl halide both react in this same step and go through a transition state, giving the products. So if you draw a graph between potential energy and the reaction coordinates, we start with both the reactants, the alkyl halide and the nucleophile, having lower potential energy. As soon as they start reacting with each other, the nucleophile starts forming a bond with the R group and the halogen starts to move away, breaking this bond with the R group. But during this bond formation and bond breaking, when it is not complete, we get a transition state, a very high energy state, an energy hill that both these reactants have to pass through to get to the products. And when they pass through this energy hill, finally energy goes down and we have the stable products. So the energy gap between the alkyl halide or the reactants and this transition state is the activation energy, which we show with this E act. This energy gap is known as the activation energy. Now let's see if there are any stereochemical outcomes of SN2 or how stereochemistry plays a role in the formation of products from a particular type of reactant. So we have this secondary alkyl halide. This is the 2-bromobutane reacting with a nucleophile, in this case a hydroxyl group. This hydroxyl group attacks the carbon that is connected directly to the bromine atom, and so as a result it will push bromine or bromide ion out of the molecule, forming an alcohol. But as you know that this is an SN2 reaction and this whole process will take place in one step. So in one step this OH attacks and in the same step the bromine would leave. But before that it will pass through a transition state. So it's a pentavalent transition state. And you can see both the OH and bromine are on opposite sides. Because of the fact that this side is blocked by bromine, hydroxyl ion or this nucleophile has only one side to attack, and that is the side from the opposite side of bromine or the halogen. And finally, when this bond between carbon and bromine breaks, we have the formation of this alcohol. And you can see here that this OH group is attached on the opposite side of the halogen. So if we start off with a molecule with our stereochemistry, we are ending up with a molecule that has an opposite absolute configuration, that is an S stereochemistry. And so we say that we have inversion of configuration. Such type of inversion of configuration is known as Walden inversion. And this Walden inversion happens because the front side is blocked by the leaving group and this nucleophile only has the back side to attack, leading to a molecule with inverted stereochemistry. Now let's see some factors that can affect the rate of reaction of an SN2 reaction. The very first thing that can affect the rate of reaction is the structure of the substrate. The substrate is an alkyl halide, but as you know already that we can have a methyl halide, we can have a primary alkyl halide, we can have a secondary alkyl halide, or we can also have a tertiary alkyl halide. I have written them in a particular order, and you can see the signs here showing that the rate of reaction is the highest for methyl halide and it is the lowest or the slowest for tertiary alkyl halide. What is the reason for this order? So we see that the methyl halide is the least hindered, and because SN2 reaction is a one-step reaction, and in this one step the nucleophile attacks and the halogen has to leave. So if the carbon to which the halogen is attached is least hindered, there will be least resistance for the nucleophile to attack that particular carbon. So methyl halide offers least hindrance to the nucleophile, while tertiary alkyl halide, in which the carbon is a tertiary carbon and it has 3 alkyl groups attached to it, is the most hindered and it offers the most hindrance to the nucleophile that is attacking that particular carbon. This methyl halide, which is the least hindered, will be most reactive in an SN2 reaction mechanism, while the tertiary alkyl halide will be the least reactive. And so it shows that methyl halide will have the highest rate. Then we see if we have different solvents, how they will affect the rate of reaction. So usually a polar aprotic solvent increases the nucleophilicity of the nucleophile, and therefore the rate of reaction will increase. Some of the examples of polar aprotic solvents are dimethyl sulfoxide and dimethyl formamide. Now, they are polar solvents and they increase the nucleophilicity of the nucleophile. So nucleophilicity is increased, and that means the reactivity of the nucleophile is increased, and therefore the rate of reaction will also increase. The reason behind this logic is that these polar aprotic solvents, they cannot solvate the anion. If we have a solvent that can solvate the anion, it will block it from reaction, or it will slow down its reactivity. But these polar aprotic solvents, they have lesser ability to solvate the anion, and thus it is freely available for attack on the electron deficient carbon in the alkyl halide. Next is the leaving group. So if we have a good leaving group, the rate of reaction will be faster. And this is logical. If the leaving group leaves quickly, swiftly, it will obviously lead to a faster reaction rate. Now, what are the factors that affect the leaving ability of a particular leaving group? Of course, it is the stability. So if the leaving group that is leaving the molecule is relatively more stable, it will be released from the molecule more efficiently and at a faster rate. For example, if we have an iodide anion, it has a larger size, the charge density is lower, and so it is relatively more stable as compared to the rest of the halide anions. So an iodide ion will happily leave the molecule, means it will take less time to leave the molecule, making the reaction much faster. Now let's see how nucleophiles can affect the rate of reaction. So generally we say that strong bases are better nucleophiles. So if we have a stronger nucleophile, the rate of reaction is faster, and this is logical, and that is related to the basicity. So if we can compare two nucleophiles, you can see here an amide anion and we have an ammonia molecule. Ammonia is a nucleophile by itself. We have a nitrogen that has a lone pair on it. But remember, this ammonia molecule is neutral. On the other hand, we have an NH2 anion, an amide anion. Now, ions, whether they are positively charged or negatively charged, are always more reactive than neutral molecules. So in this case, this NH2 anion is more reactive than NH3 stable molecule. That is why this anion is a better nucleophile, giving a faster rate of reaction than ammonia. Then we have the comparison between hydroxyl anion and water. Water can act as a nucleophile, but it's a neutral, stable molecule, while hydroxyl ion is an anion, and of course it will be less stable and more reactive. And then we have fluoride anion and HF. Fluoride again is a highly unstable anion and will be more reactive. So comparing anions with neutral molecules, you will always say that the anions are more reactive, stronger nucleophiles, giving faster rate of reaction. But what if we compare these three anions among themselves? So going from fluoride anion to amide anion, going through hydroxyl anion, we are actually increasing the basic strength of the anion. So as you saw here, strong bases are better nucleophiles. So if you are increasing basic strength, you are actually increasing the nucleophilicity of these anions. That means that this NH2 anion is a better nucleophile, while fluoride anion is a relatively less good nucleophile. That is why the rate of reaction will be the fastest with amide anion, then hydroxyl anion, and finally fluoride anion. So these are some of the facts about bimolecular nucleophilic substitution reactions. We will discuss some more substitution reactions in the upcoming videos. So stay tuned and thank you so much till then.